There are a lot of ways to build a clock circuit for our computer, but we want something that's relatively flexible. We can adjust the speed. We don't want it to run too fast. We want to be able to see what's going on. And so I'm going to use the 555 timer. This is a classic integrated circuit here, the 555 timer, and that's what this chip is here. And so you can tell pin 1 here is by the divot, and 1, 2, 3, 4, 5, 6, 7, 8. And right now I'm powering this with, this is just 5 volts coming in from a cell phone charger that I've cut into the USB cable and pulled the 5 volts out. And to power the chip, power comes in 5 volts here on pin 8 and ground to pin 1. You can actually go up to, I think, 17 volts or 16 volts or something with this chip, but 5 volts works. And to control the timing, you've got 2 resistors and a capacitor. And so the first resistor here is going from 5 volts to pin 7. This is a 1K ohm resistor. And then from pin 7 to pin 6, I've got a 100K ohm resistor. And then pin 6 is connected around to pin 2. And then from pin 2 to ground, I've got this capacitor, and this is 1 microfarad capacitor, and you can see the positive side is connected here to pin 2, so the negative side is connected to ground. You want to make sure that's in the right way. And so those resistors and the capacitor control the timing. We'll see how that works in a minute. But the output of this chip is on pin 3, and so that's just connected to this LED. And the output can drive a fair amount of current, so we want to make sure we have a current limiting resistor. This is just a 220 ohm resistor here limiting the current through the LED so we don't burn up our LED. So how does it work? Well, a good place to start, of course, is the datasheet. This is the datasheet for the 555 timer, and you can see they actually give you a whole schematic of what's going on inside that chip, which we won't go through all that. But they also give you a bunch of other stuff in here. One is this sort of block diagram that gives you a little higher level view of what's going on, and so you can see there's a couple comparators. There's these 3 resistors. There's a flip-flop that these comparators connect into, and then there's this output stage. So this is pretty interesting. I don't personally like the way that this is drawn. It's kind of drawn to line up with the pins here. They give you a different version of it a little bit later on in here. This is a sort of a different view of the same thing, but I don't really like this one either. It doesn't show there actually should be a connection from here to this comparator, and you don't really know what these inputs are. It's like, okay, there's 3 things going into the flip-flop, but what are they? I don't know. I don't particularly care for these diagrams, so I drew up my own that I think explains this a little bit better. And you can see, just like those other diagrams, there's the 2 comparators. There's a flip-flop. It's actually an SR latch. I think it's probably a better way to describe what this thing is. And we can just kind of walk through what's going on here. So everything inside this blue box here is kind of what's going on inside the timer itself. And then the green stuff that I've drawn out here is the rest of the circuit. So we can kind of go through and look at what we've got. So this is a 1K resistor going from 5 volts to pin 7. And then between pin 7 and 6, that's this 100K resistor here. And then you can see pin 6 and 2 are connected. That's this little green wire going around here. And then between pin 2 and ground, we have this 1 microfarad capacitor. And then over here we just have our LED, and this is our, I think it was a 220 ohm resistor over here. So this is our circuit. And to understand how it works, we can kind of look at what's going on inside the 555 timer. So just start by looking at this path through here. You can see we've got our plus 5 volts up here. And then of course our ground down here is 0 volts. And then there's these 3 resistors, and I think each of these resistors inside here is 5K. So 5K, 5K, 5K. I think it's a complete coincidence that it's a 555 timer, but anyway. But what these do is these set up a voltage divider. And so at this point here, you've got 1/3 of the voltage between 0 and 5 volts. So that's 1 2/3 volts. So 1.67 volts we'll call it. And then at this point here, we've got 2/3 of our 5 volt supply. So this is 2/3 is 3.33 volts. And so you've got this voltage divider. So you got 5 volts, you go through this resistor, you're down to 3.3, you go to this other resistor, you're down to 1.6667, whatever. And you go through this other resistor and you're down here at ground at 0. And what that does is that sets up these inputs for these comparators. And the way the comparators work is there's a positive input and a negative input. And if the positive input is above the negative input, then the comparator switches on and the output is 5 volts. And if the positive input is below the negative input, then the comparator switches off and the output here is 0 volts. So let's think about what happens when we turn this thing on. Get this out of the way here for a second. So what happens is, let's assume that these inputs over here, this is all 0 volts. So we've just turned this on, the stuff is 0 volts. So we've got 0 volts coming in here, that is below 1.6 volts. And so this comparator turns on. And so that triggers the set pin of our SR latch. And if you don't know what an SR latch is, I've got a video on that, but basically it's got a set and a reset. And when the set goes high, then the output comes on. And when the reset goes high, then the output turns off. And then of course, if they go low, then it remembers its last state. And there's both the output here, and then there's the inverted output here, which is always the opposite of our output. So if we have 0 volts here, we got 0 volts here, this comparator will be on because 0 is below 1.6. And this comparator will be off because 0 is not above 3.3. So this one's off, this one's on, and so the latch is going to be set, which means our output will be on. So the LED will be on. So we're going to start on. So we'll do a little graph here. And if our output is on, then our not output, our inverted Q here is going to be off, and so this transistor will be off, and so nothing's going to go happen here. We can kind of ignore this whole discharge thing here for now. So what's going to happen is we're going to have current flowing through this 1K resistor, through the 100K resistor, and into this capacitor down here, this 1 microfarad capacitor. And that capacitor is going to start to charge. And so if you look at the charge on the capacitor, which is also the voltage here going into pin 2, it's going to start, move this, so we can see here, it's going to start here at 0 volts and it's going to start to climb. And it's going to keep climbing and climbing and climbing as this capacitor charges. And so what's happening is the voltage here is increasing. And at some point it's going to increase above 1.6 volts. And if it's above 1.6 volts, this comparator will turn off because 1.6 is no longer above whatever this voltage is. So this comparator turns off, and that's fine, right? Because the latch is going to latch its output. So we're not asserting the set pin anymore, or this set signal. But you know, if we haven't reset it yet, we're still going to have a high output here. But eventually, this voltage is going to reach 3.3 volts, and it's going to maybe go a little bit above 3.3 volts. And at that point, you know, that voltage is going to be above 3.3 volts, and this comparator will turn on because the positive input here is above the 3.3 volt negative input. And so this will turn on, and this will reset the latch. And I guess I didn't give myself enough room here, so ignore that. So this is our output. Our output is going to get reset when this hits 3.3 volts. So, so if this is like 3.3 volts on our capacitor here, maybe this down here is 1.6 volts, and then we'll say this is 0. So we started at 0, we went through 1.6 volts, you know, nothing happened, we turned off the set pin, but we stayed latched. And then we get up to 3.3 volts, and at that point our output turns off. But the other thing that happens is our not output, our inverted output, this turns on. And that's going to cause current to flow from here through into the base of this transistor, and that'll turn on this discharge transistor. And so then what happens is, you know, current can now flow through the 1K resistor, through this discharge to ground. So, okay, that's not very exciting. But what's more interesting is that current can also flow from the capacitor through the 100K resistor. You know, so before we were charging the capacitor in this direction. Now we're discharging the capacitor. Current is flowing from the capacitor through the 100K resistor and through this discharge. And so the capacitor is going to start to discharge. And it will discharge for a little while. And of course, it'll, you know, as soon as it starts discharging, it'll drop below that 3.3 volts. And so the reset will turn off. But again, this is latched, so nothing happens. But eventually, the capacitor's voltage will drop below 1.67 volts. And now, with this below 1.67, the set comparator turns on, and it sets the latch again. And so when we set the latch, when this gets down to 1.6 volts, we set the latch, we turn the output on. We also turn the discharge transistor off. So we turn this off, and so we're no longer pushing current through the base of this transistor, so this transistor is off. And so no longer is the capacitor discharging, we're back into this state where the capacitor is charging again. So the capacitor will charge, our output is on, eventually the capacitor will get back up to 3.3 volts. This will switch, we'll start discharging again, and this will turn off. Capacitor will discharge, and it's off. Capacitor will charge, discharge, and so we get the capacitor is charging and discharging kind of like this, but our output here is this nice clean square wave. And that's what we see when we look at the circuit here. We see our LED flashing. And of course we can control the rate that the LED is flashing based on the values of these resistors and the capacitor, right? Because you know the rate is set by how quickly this capacitor charges and how quickly it discharges. And so how quickly it charges is going to be dependent on these two resistors and the capacitor. So the bigger these resistors are, the slower it's going to charge. And of course, the bigger the capacitor is, the longer it's going to take to charge. And then if these resistors are smaller, then it'll charge faster. If the capacitor is smaller, it will charge faster. And then for discharging, so the time when this is low, it's just discharging through the one resistor here. And so, again, if this is a bigger resistor, it'll take longer to discharge, and so this will be low for longer. If it's a smaller resistor, it'll be faster. And so by adjusting these components, we can kind of control the rate here. And so one thing you might notice is that, I chose a 100K resistor here, and then a relatively smaller 1K resistor here. I mean, this is only 1% of this. And that's because, because we're charging through both, and when we're discharging, we're only discharging through this one. But I wanted this square wave to be fairly symmetrical. And so by this only being like a 1% difference in the charging from discharging, you end up with essentially the same time that it's off that it is on. It's sort of what's called the duty cycle. And if you look at the data sheet, they actually give you some formulas here for figuring out the time that it takes to charge or discharge. So charge time, discharge time, and they actually show a nice little graph that looks very similar to the one that I just drew. But you can see, they give you the charge time is based on RA plus RB. I think they're calling this RA and this is RB, times the capacitance, which is the C here. Whereas the discharge time is just based on RB, right? Because we're only discharging through that one resistor, so you don't see RA in there. And then the total period is RA plus 2RB, right? Because it's RA plus, you're going through RB twice for the total period times our capacitance. And so we can figure out our total period just using this formula. We can pull out a calculator here, and so just sort of order of operations here. Resistor B is 100,000 ohms, so times 2. And then we can add in resistor A is 1,000 ohms as our 1K resistor. And then we'll multiply that by our capacitor, which is it's a 1 microfarad capacitor. So I think that's 1 microfarad. And then we multiply that by this 0.693. And the reason you're multiplying by that is, the resistance times the capacitance gives you the time constant, and that's used in to sort of give you this exponential. Can't see what I'm doing here. The curve for this exponential function. But we're not going the whole way, and we're just going from 1.6 volts to 3.3 volts, and so they've done some of the math for you to figure out what coefficient to use to get from the time constant to the actual period. And so what we come up with is 139 milliseconds, or 0.139 seconds. And so that's the period that our LED is flashing. Now if we want, we can double check all of this for ourselves by hooking up to an oscilloscope here. So I'll just hook up the ground for my probes here, and then I'll connect one probe to the output, which is the pin 3 here. And then I'll hook the other probe up to the capacitor. So we can watch the charge on the capacitor. And here we go. We can see our output, which is this nice square wave, and then we can also see the charge and discharge of the capacitor. And so if you look, 0 volts is down here. So this is 1, 2, 3, 4, 5 volts. So you can see the charge and discharge of the capacitor is going from You know, this is about 1 2/3 of a volt up to, you know, 1, 2, 3 and a little bit, 3 1/3 volts. So exactly what we'd expect from that, you know, that voltage divider. Now the output you see is going from, you know, 0 volts here to 1, 2, 3 and a little bit here, 3.5 volts maybe. And you might expect it to go all the way to 5 volts, but actually the datasheet does talk about this. It does say, if we look at the output voltage here for 5 volt, it says typical is 3.3 volts, and we're getting, you know, a little bit more than that, but it says the minimum is 2.75 volts, so we should be getting at least a minimum of that, which is fine. That's enough for a logic high level, so if we're feeding this into any kind of digital logic, we'll be okay with that. And then we should see, you know, 139 milliseconds here, so this is 50 milliseconds per division, so this is 100, 200, and so that's not quite, not sure why. I'm gonna double check this. Well, I figured out the mystery. So we calculated 139 milliseconds and we were seeing about double that. And the problem turned out to be these capacitors. So, you know, looking at this capacitor, it says 1 MFD 50V. So I would assume that that means it's a 1 microfarad capacitor, 50 volts. It's got this 1022. I assume that that's a date code of some sort. Maybe it's manufactured in 2010, the 22nd week of that. And that's all it says on it. So I would assume this is a 1 microfarad capacitor. Turns out, when I hook it up to my meter, it measures at 2 microfarads. So I don't know what's going on with that. I got a whole bucket of these things, and they all say 1 MFD on them. And they all, or at least all the ones I measured, measure 2 microfarads. So instead of 1 microfarad, it's 2 microfarads. And so, you know, if we plug that into our formula, we had 1 microfarad there. Instead of we plug 2, we're basically multiplying by 2. So multiply that by 2, 278 milliseconds. And, you know, we're measuring 263 milliseconds period here, and that's much more in line. That's certainly within, you know, we've got 5% tolerances on these resistors and stuff. So 263, 278, close enough. So very interesting. I always assumed these were 1 microfarad, but apparently not. If anyone knows why they're marked that way, maybe I'm missing something obvious, but I would assume that 1 MFD means 1 microfarad, but apparently 1 MFD means 2 microfarads. Go figure. Yeah, so 263 milliseconds, that's much more what we'd expect. And so if we take 1 over 263 milliseconds, we get about 3.8, and so that tells us this should be flashing about 3.8 times per second, and that, I don't know, visually seems about right. So I think we're almost done with this circuit. It looks like it's working. I did want to talk just briefly, there are some power supply recommendations in the data sheet, and I wanted to talk a little bit about the power supply. We've got, this is just a cell phone charger. This is from Apple, which is actually a very good power supply if you get a genuine Apple one. But in any event, you know, it looks like everything's working fine. You know, our LED is flashing. We've got our nice clock output here. So you could probably use this and it would work okay, probably. But there are a few things that the datasheet recommends doing to reduce noise. And so one thing it recommends doing is putting a capacitor on pin 5. We're not using pin 5, it's control voltage, it's for some other features of the 555 timer that we're not using. And it recommends putting a 0.01 microfarad capacitor from pin 5 to ground to reduce noise. So what is it talking about? Well, we see on the scope here, we see this nice transition from 0 volts to 5 volts, but if we zoom in on that, or zoom in, what you see is that nice transition from 0 volts to 5 volts is maybe not so nice. There's a lot of junk in there. So if we add this capacitor that they're recommending from ground to pin 5, boom, clears it right up. So definitely recommend that. 0.01 microfarad capacitor going from pin 5 to ground. There's still some other noise if we go in even further. Go into, oh, I'm going the wrong way. Go all the way into nanosecond range. You see there's some overshooting here. And what's happening is when the output wants to turn on, you know, there's a bunch of transistors in here switching and doing whatever they do. And, you know, when they switch, you know, there's a different current requirement. So they're pulling more current, or they want to pull more current from the power supply. And they're not able to pull that current as quickly as they would like to, and then at this point they end up getting more current than they wanted, and it kind of overshoots. And I'm surprised we don't see more sort of back and forth oscillations here. That's fairly typical, but it looks like it levels out pretty quickly here. But we're overshooting above, right here. This is 5 volts. We're going up over 6 volts, which may not be good. If our output is supposed to go between 0 and 5 volts, and we're feeding into something that's expecting 5 volts, and we give it 6 volts, that could be a problem. And the reason that this is happening is, our power supply is over here, and we've got all this wire that's connecting it to the board. And you say, well, the wire is just it's a conductor, just electrons flow right through, no problem. Well, almost. In a perfect world, sure, that's how wire would work, but we're not in a perfect world, and so this wire has some impedance. It's actually acting as an inductor. So when you run current through the wire, you get a magnetic field that builds up around it, and that magnetic field is going to resist changes to the current that flows through that wire. And so when we try to pull more current, we get a little bit of an impedance that's resisting that. And so I can demonstrate this by getting all of this wire out of here and hooking up this short USB cable that I've hooked up, and plug that in. And there you see, this comes up a lot faster, is one thing you'll see. And you also see it doesn't go above 5 volts. Still doesn't, it takes a little bit of time to settle in, but this is much better. We're staying in spec. We're not going above 5 volts. It's turning on pretty quickly. And that's just because we don't have all of the impedance in this wire. We do still have impedance, from here through the traces inside this breadboard, and into the chip and everything. So it's still not perfect, which is why it doesn't look perfect here, but a lot better. But of course, we don't want to have a short little power cable like this. We want to be able to not have our extension cord run all the way up to it. So let's plug this back in and see what else we can do. So we're back to that crazy overshoot. The other thing we can do is if we put a capacitor just across our power connection here, that capacitor can sort of get charged, and then when this chip wants to pull more current, it can pull it from the capacitor. So if we just take this is a 0.1 microfarad capacitor and just stick it right across those power pins, boom, we get basically the same thing. And that's because the power supply has capacitors in it. It's doing essentially the same thing that we're doing with this capacitor here. Now ideally, what you'd want to do is you'd want to get this capacitor as close as possible to the chip and put it right across the power pins on the chip. And if you look in any electronics, every chip is going to have a capacitor or maybe multiple capacitors sitting right next to it to smooth out these current transitions. I'm not going to get too crazy with it. I think, with this computer we're building, we're not running at a super high speed. So if it takes a little while to come up and stabilize, it's, not too big a deal. So what I'm going to do is just put one of these little 0.1 microfarad capacitors on each breadboard, and hopefully that'll be good enough. Okay, so we've added our 0.01 microfarad capacitor here to pin 5. And we've also got a 0.1 microfarad capacitor just sitting across our power pins. And so I'm going to move that over here just so it's a little bit more out of the way, but it's still connected to the board across the power pins, which I think is good enough. But there's one other thing that the datasheet recommends, which is pin 4, which we don't have anything connected to. And I didn't draw it on the diagram here, but what pin 4 is it kind of gives you this other connection here to the reset of the latch. So it gives you kind of a direct connection in here to just reset this latch if you wanted to. And actually, I should draw it. It's inverted input. It's not hooked up exactly like this, but this is basically how it functions. Is if you bring pin 4 low, it'll just force this latch to reset. It overrides anything that's going on over here. So normally we wouldn't want to bring that low unless we wanted to reset this. And so what the datasheet recommends doing is to prevent it from accidentally, going low if there's some stray voltage or something. It recommends, if you're not using it, to just tie it to 5 volts. So if we just connect that to 5 volts, then this will always be high, which means we're not going to be, inadvertently resetting this if there's just some noise. So that's just something else we'll do. And then the last thing I wanted to do is I want to be able to control the speed of this thing. So we have it blinking at this, 3.8 times per second or whatever it is. which is great, but it would be nice to be able to control it. And of course you can change out the capacitor, change out these resistors, and you know, hopefully you can kind of see how to do that. But what would be really nice is to add, you know, change this 100K resistor to a variable resistor. And so I have this 1 mega ohm variable resistor, and you just turn this and get a different resistance, and it goes from 0 ohms, so just a short, all the way through 1 mega ohm, which is 10 times more than this. And so what we can do is we can add this to the circuit here, and what we can do is we can hook that up in place of this 100K resistor. So if I take the 100K resistor out, and then what I'll do is just hook up some jumper wires from you know, pins 6 and 7, right? We want to connect between pin 6 and 7. And I'm just sticking it over here with these jumper wires because this is too big to just jam right in there like the little resistor was. But the other thing I'll do is I'll put it, instead of just hooking this variable resistor between pins 6 and 7 by itself, you know, because when you turn it down, it goes down to 0 volts. That would be a direct short between 6 and 7, which would mean that when our clock turns off, the capacitor, instead of discharging like this, the capacitor will discharge almost instantly through here if there's no resistor there at all. And so then, you know, basically this would never go low, because as soon as this goes low, it would instantly, almost instantly, go high again. So we don't really want that. So what we can do is we can put another resistor in series with our variable resistor, and that'll you know, essentially act as a minimum value. So I'm going to put in this 1K resistor between the other pin of our variable resistor and pin 7 there. So, you know, if this is turned all the way down, it's 1K, and if it's turned all the way up, it's 1 meg or 1.001 meg or whatever it is. So let's hook that up again and see what we get. And it looks like it's on. Oh, there it goes. Yep, it's just going really slowly. And of course we can turn this knob and get it to go faster. There, it's going a little bit faster. And we can turn it even more and it goes even faster. And if we turn it all the way, it's, I don't know if you can see that. I can see it's basically flickering because it's just going so fast. Because right now, with this turned all the way down, we just have a 1K resistor. And so when it's charging through 2K of resistors, and then it's discharging through 1K. And so you could probably do the math and figure out how fast that's flashing. But I like that. And I can get it kind of dialed into whatever speed we want. If we want to go really slow, you know, again, we're using this as a clock for a computer, so we may want to go really slow to see exactly what's going on. We can do that. But we might also want to just manually control the clock by pushing a button, so we can go as slow as we want. And so we'll look at that in the next video.